how in the classical world something appears or represents whatever might be happening in the quantum world, one way or another. That's what measurement is about. You want to retrieve something. And in the quantum mechanical formalism, there is no such thing as classical data. It doesn't exist within the formalism. It lives outside of the formalism. Like what? Give me the state of classical data. It doesn't exist in quantum mechanics. It's just not a comprehensive formalism from that perspective. It's not a comprehensive formalism. So it's actually a really bad setting to think about how classical can interact, because there is no classical in the formalism. It's informal. What do? You diagonalize a matrix, and then you calculate the probabilities, and then you say, yes, with implicit in this diagonalization process, you assign a classical outcome to one of the elements of the spectrum. But this is not part of your Hilbert space. This is something informal you do on top of it. So in what I write down here, I assume that the classical data will be part of my formalism.
The measurement problem.
What?
The measurement problem actually is that the measurement apparatus should be quantum system also. And how comes it down that we can?
I'm not saying that it is a quantum system. I'm just saying that the data lives in my formalism. I'm not making any philosophical statement whether the measurement should be quantum system or not. I'm just saying I want my classical data to be part of my formalism because I'm talking about it.
I'm fine with that, but then you simply avoid the discussion of the measurement.
You avoid?
You avoid the discussion.
Yes, I try to avoid as much as possible anything which is speculative. And the thing is, I'm trying to do much more at one time, and I'm not going to. But I want to avoid the typical sort of parts where distinct opinions might arise.
Yeah.
And I'm going to try to get as far as possible without saying anything there. Now, as we will see, there will, and actually I only realized this yesterday, in this setting there will actually be a result, which is a purely mathematical result, which doesn't go with taking assumptions like how do we describe the measurement operators, but there is a result about the measurement problem. We'll see that. And especially about the role of the observer. I only realized this yesterday when somebody asked a question about the observer. It was you, I think.
Yeah.
So anyway, so these are two operational things which I've never seen in physics literature, that you want these things. Compositionality, which is so obvious, that if you've got a composition in your mathematical formalism, that it would mean something physically, as just doing one and then doing the other. Tensor product means one and the other, in parallel. So you've got these two dimensions to composition. You've got tensor composition in parallel, sequential composition in time. And this is like a two-dimensional structure, which is, for example, not present in direct notation. That's why actually you end up doing pictures. Pictures is just the mathematical representation of a two-dimensional structure. So it's not pictures because it's funny, it's because pictures because your structure requires it. Okay, so just quickly, so we're going to re-axiommatize quantum theory in terms of the tensor structure alone, so there will be no such a thing like an a priori number field or numbers or anything like that. There won't be sums in a product, say, priori. There won't be an algebra of observables. It's all gone. And physically, this means you don't take probability and statistics a priori, while a lot of axiomatic approaches actually do this. We don't care about that initially. It will all come out. No such thing as superposition, orthogonality. No such thing as observation, measurement tests. These things we hope to come in later, or be definable within the setting, but we don't assume this a priori. So, basically, the formal theory, while it will be axiomatized in abstract categories, I'm not going to talk category theory today. I'm just going to talk pictures. Because there is an amazing thing about the categories which I'm going to use, is that you can prove meta-theorems. They're really hard to prove, but that anything you can prove in the algebra, you can derive in some topological graphical picture calculus. Equivalently. So if it's true there, then it's true there. So it's just a different mathematical language for the same thing. And so you've got this nice picture here. So the reason I use categories is because the operational foundation, I want the types and I want the compositionality. And I'm going to derive that how you do it. There is this really nice thing that you get a purely graphical calculus which extends Dirac notation. So which gives actually formal status to Dirac notation and also extends it at the same time. And these categories actually are there in traditional category theory. They are exactly used to encode logic. They are semantics for logic. They're not partial order semantics, they're categorical semantics. The difference between categorical semantics and partial order semantics logic is that if you have in a partial order, A is less or equal than B, and typically you want to read it as A implies B. If A is true, then B must be true. Now what categorical semantics does to that, it says there is an arrow from A to B. And basically it says, if A is true, then by means of F I can derive B. So it gives you a formal witness of the process of going from, listen, it gives you a formal witness of the process of going from A to B. That's what categorical semantics is about. It gives you formal witnesses. This is about truth. This is about provability. Now, provability in physical terms will be processability. You can transform something to the other by physical means. Like in logic it means by mathematical calculation. So this would be by mathematical calculation. If I assume A, I can derive B. So it's a nice analog between these fields. So, as I said, these pictures are not just in illustration, but they're actually a formal proof, and it extends direct notations in a two-dimensional way by distinguishing between these two modes. So, you can also think of it as a sort of theory about information flow. Again, importantly, this is measurement. Quantum classical is measurement. But there are much more important, there are other important information flows in physics. For example, classical quantum. You do classical quantum information flow. I decide to, if I can do a bunch of unitary transformations, say this has been in quantum informatic perspective where you apply gates. They say you apply a logic gate, which means I apply a unitary transformation. Then, depending on some set of data, you could choose one or the other. So this is a flow of information from classical to quantum, not just from quantum to classical, from classical to quantum. But this is something which is, of course, not at all in the quantum mechanical formalism. Not to speak about classical flow. The classical flow is an important part of our world, you know. It's like it is. It's like so you've got this whole control structure here. This is quantum measurement. It's the only thing people have been caring about in foundational physics. But then you've got this quantum flow. So you've got this whole complex of flows, classical. So here is classical, quantum, classical. And the only thing people just look at one, typically. So you want to do. So anyway, this is going to be the outline of my talk. I hope. I took a long time for this introduction. So the first part will be operational account on compounders. And this will be extremely general. We won't have to do anything with quantum mechanics specifically. Then part 2, quantum compounders. What is more specific about quantum mechanics than any other situation where you consider two things as one? And then the third part will be how classicality and measurement arise within this setting. By just that was the start of my talk. That I said the Norman thought measurement is the key to axiomatics.